Hi, everyone. I'm Shivendra Kushwa from UC Berkeley, and I'll be presenting PSec, Programming Secure Distributed Systems Using Enclaves. So, distributed systems are essential to modern computing. The ability to break a computationally complex task into multiple parts and divide the workload leads to more efficient computing as well as more maintainable components. Due to this importance, many domain-specific languages have been developed to enable programmers to easily create these kinds of systems. However, programming secure distributed systems is still an active area of research. Generally, lower-level programming languages such as C, C++ are susceptible to attacks such as buffer overflows. Higher-level languages usually still require knowledge of crypto primitives to properly initialize crypto libraries for critical operations. Taking a broader look, in the distributed setting, using proper cryptography is critical to transmit secure messages. However, even if the message is sent securely, there are no guarantees that the receiving machine will not accidentally leak the underlying sensitive data to adversaries. Looking at current literature, we see a variety of approaches. Language-based information control approaches tackle this problem by enforcing policies on sensitive data passed through the system through information flow control type systems. A main assumption behind these approaches is the correctness of the trust designation system, which requires entities to specify which nodes they believe to be running compliant code. Another type of approach leverages trusted execution environments, such as Intel SGX. These approaches reduce trust assumptions on hardware and operating systems, but a lot of these approaches do not lend themselves to be easily usable by programmers, nor do they provide sufficient protection against accidentally leaking sensitive data. In our work, we seek to combine the aforementioned lines of research and create a programming language that provides the right level of abstraction and enables programmers to easily write secure distributed applications. We present PSec, a state machine-based programming language for creating secure distributed systems with an information flow control type system to prevent secure data from being leaked to untrusted systems or being maliciously corrupted. We present a runtime that leverages SGX to enable the secure creation of machines and the ability to securely send messages between them. We also create a trust designation system in order to establish trust between state machines. Finally, we've implemented a variety of examples to demonstrate language expressiveness and measure our language overhead to be approximately 3x for longer running systems with a possible minimum of 1.2x. Now for some background. P is a programming language based on concurrently executing state machines communicating via messages. Programmers write high-level P code, and the compiler will generate executable C code. For context, P has been used to develop the USB 3.0 driver inside Windows 8.1 and is currently being used inside AWS to build reliable distributed services. Given its easy-to-use nature and ability to express complex distributed applications, P serves as an ideal base to build from, and we found it to be readily adaptable to target the creation of secure distributed systems. The main language ideas behind P are programmers can create state machines dynamically, and each machine can send events containing payloads to other machines. Programmers can then define various event handlers for the machines so they can execute actions and make state transitions when receiving incoming events. Now, here's an example of a sample P program. In this example, we have a server state machine on the left and a client state machine on the right. As you can see, the client machine goes ahead and creates an instance of the server machine and raises a success event. This event leads to a state transition to the send ping state, where it sends a ping event to the server. This event actually contains a reference to itself, also known as a machine handle. The server machine receives this and sends a payload, which in this case is the client machine, a pong event. These sequence of events keep repeating, and this example is known as the ping pong example. Now, shifting gears a little, I'll be talking about enclaves. So enclaves are a protected region of memory where application code can run securely. The content of enclaves are protected from all other processes, including the OS, and is only decrypted on the fly by the CPU to run commands. Enclaves have to interact with their untrusted hosts for functionality that cannot be performed within the enclave, such as making network calls. Attestation is also a major enclave feature, and this provides a way to verify that the enclave's code has not been tampered with. Finally, Intel SGX is a popular enclave technology, but writing Intel SGX code is non-trivial. For example, a bare bones version attestation using the SGX SDK requires almost 1,000 lines of C++ code. Now, I'll introduce the PSec programming language. First of all, we wanted to create language constructs that enable programmers to implement real-world systems. Secure distributed systems, which consist of trusted entities, may have to interact with external untrusted entities for input or to execute non-sensitive tasks. We enable this by allowing programmers to choose between two types of PSec state machines: secure state machines, or SSMs, and untrusted state machines, or USMs. SSMs are trusted run sensitive code and hold sensitive data, and they're typed with the secure machine keyword. USMs run in an untrusted world and are typed with the machine keyword. Since PSec machines are created dynamically, we need a way to securely create state machines on the fly. In addition to this, we need a way to designate trust so that state machines are confident that they're communicating with trusted entities. Note that we define trust in the following way. If A trusts B, A assumes that B will not leak any sensitive data, nor send any malicious inputs. For trust designation, our initial approach had SSMs trust all other SSMs running valid PSec code. However, this designation of trust is too broad because adversaries can easily perform denial of service attacks on self-hosted PSec machines, and our machines would be waiting on responses that will never come. A better approach is to have trust chains centered around machine creation. The primary driver of trust is that SSMs trust any SSMs they've created, and these child SSMs trust their parent SSM. The secondary driver of trust is through trust designation. Child SSMs additionally trust SSMs deemed by a fellow trusted SSM to be trustworthy. Based on this, in terms of machine creation, we have two cases. We have a trusted create when an SSM creates another, and we have an untrusted create for all other use cases. To elaborate on the different types of creates, for trusted create, this results in the parent SSM receiving the handle of the newly created SSM so it can communicate with it, as well as the capability to send sensitive data or trusted messages to it. This is all indicated by the secure machine handle typed object. The parent SSM can share this capability by just sharing this secure machine handle. We also have untrusted create, where the parent machine receives the handle of the newly created machine. This is indicated by the machine handle object. In the diagram, you can see both a trusted and an untrusted create operation. In this case, the @ command indicates which physical host the machine should be created on, which in this case is the same physical host as the parent machine. We define two types of message sending. We have trusted message sending, which enables exchanges of potentially sensitive and trusted data between trusted SSMs. The specified machine handle in this case needs to be secure machine handle. We also have untrusted message sending. This is to cover all their use cases. Messages, please note that messages are still sent securely, but since the messages may originate from the untrusted world, the content of these messages are untrusted. Since messages need to be encapsulated by event objects, we also define trusted events, which can only be sent through trusted message sending, and untrusted events, which can only be sent through untrusted message sending. We finally defined other language commands that we found to be useful while implementing a variety of real-world examples. Our seal command enables programmers to encrypt data in SSMs, such that only instances of that specific SSM are able to decrypt it. And this is useful in cases when the SSM wants to store extensive data on the untrusted host machine. We also define a local authenticate command. This allows USMs to verify that any SSMs running on the same distributed hosts are actually running valid or expected code. This is necessary to establish a one-way trust from a USM to a particular SSM, since we already have mechanisms to establish SSM to SSM trusts. Now, I'll be talking about PSec's information flow capabilities. So first of all, why do we even need information flow analysis? So we need to prevent sensitive data from being inadvertently leaked by the programmer. For example, if the programmer encapsulates SSN information in an untrusted event and sends it to the untrusted world, this would be a huge disaster. Programmers should be able to indicate which data is sensitive, and the language type system should provide protections. To implement information flow analysis, we can augment our type system to include security labels for each type of variable, H or L. Programmers can mark variables with a secure type corresponding with H to indicate they contain sensitive data. We need to propagate these labels as variables are added, assigned, and enforce certain rules to prevent the data from being leaked. The adversary model is that we are assuming the adversary can view or infer the content of L security variables and expressions at any time. And given this assumption, adversaries should not be allowed to infer the value of H security variables or expressions. The high-level goals, once again, are, to state it a little more explicitly, the high-level goals. Number one, we need to be able to correctly classify expressions. For example, an expression is H if it contains any H variables. Number two, we need to be able to prevent explicit flows. For example, we need to forbid H expressions from being assigned to L variables, since the adversary can view the content of any L variables. Number three, we also need to prevent implicit flows. For example, we need to forbid commands with hguard from assigning to L variables, since this would be a side channel to the value of H. In PSec, the main ideas of IFA are untrusted events should not contain any data with high security labels. Operations exposing sensitive data through implicit flows should not be allowed. And also, we do provide for an endorse in a declassify function to enable the programmer to explicitly change security labels to send data so that they can retain the flexibility to implement real-world examples. We provide justifications for this in the paper. Here's a quick example of our information flow analysis. As you can see, the state machine can take different actions based on trusted events and untrusted events. If you quickly look at line 14, you can see that the sensitive value needs to be declassified before being sent through an untrusted event. For adversaries, we assume that there are different levels of adversaries. First type is a passive network observer, and we assume they can observe all network traffic. The next type is an active man in the middle, and they can additionally tamper with the traffic. Finally, we have a privileged attacker who can additionally corrupt host machines and spin up malicious enclaves. They have privileged access in the untrusted world and can tamper with all internal state for the host machines, except for state stored within enclaves. PSec provides different guarantees against each type of adversary. For the passive network observer, PSec uses crypto to prevent network observers from determining message payloads, but the adversary can still determine which two parties are communicating, as well as message types and lengths. For active man in the middle, PSec enables state machines to detect if any message payloads have been tampered with, but adversaries can still perform denial of service attacks. Finally, for privileged attackers, they can actually send authenticated messages from compromised parties to other state machines in our system. However, since PSec prevents SSMs from ever giving secrets to the untrusted world, sensitive data cannot be leaked this way. Malicious enclaves spun up by these attackers will additionally not be trusted and therefore won't receive any secrets. Now, for our language implementation, we created the PSec secure runtime and the PSec untrusted runtime. The secure runtime resides inside an Intel SGX enclave and is responsible for executing the SSM inside the enclave. And it also additionally implements all of the necessary functionalities for our various constructs. The PSec untrusted runtime is in charge of USMs and additionally ferries messages to the network for all of the state machines. As part of our system architecture, we have distributed host machines and a trusted key provisioning server, or KPS. Each SSM and USM will have an identity public-private key pair, but SSMs additionally have an associated capability key. As you can see in the diagram, SSMs are hosted within the PSec secure runtime, while USMs are hosted within untrusted memory. The KPS attests enclave code, and it also generates capability keys upon new SSM creation. The KPS also provides network address lookup for various machines in our system. Now, we'll talk about some of the PSec protocols. So the trusted create protocol is used for SSM to SSM creation, and outputs a secure machine handle typed object. For a high-level overview, SSM1 sends create SSM request to distributed host 2, and its PSec trusted runtime creates SSM2 and attests with the KPS to register it and receive its capability. Distributed host 2 sends back to SSM1 the SSM2 public identity key, and finally, SSM1 attests with the KPS and retrieves the SSM2 capability. It then wraps this as a secure machine handle and returns this back to the programmer. This is all outlined in the diagram below. The PSec Trusted Send protocol is invoked when an SSM wants to send a message to another SSM. Essentially, when the sending SSM invokes the send command with the secure machine handle, the PSec secure runtime generates a session key, encrypts it with the receiving SSM's identity key, and sends it over. As a quick overview, it then essentially serializes the PSec event payload, sends over this with the receiving SSM's private capability key, and sends this entire chunk encrypted with the session key over. Essentially, the sending SSM authenticates using the capability, while the receiving SSM authenticates using its identity. We implemented a variety of examples using PSec to demonstrate the expressiveness of our language, which are outlined in the paper, but for brevity, I will just go over the one-time passcode example. In this example, we have a bank SSM, a client web browser USM, and a client SSM. In the setup phase, the client web browser USM authenticates with the bank SSM and requests to enable two-factor. The bank SSM then creates a client SSM on the same host as the client web browser and provisions it with the master secret, which we mark as secure. In the sign-in phase, the client web browser sends a request to the client SSM with its credentials and receives an OTP code in return. This OTP code is a function of the input credential and is generated regardless of the correctness of the input credential. Afterwards, the client web browser forwards this code along with its credentials to the bank SSM. The bank SSM sends back either auth success or auth failure, and the client is either successfully logged in at this point or redirected to log in again. Finally, we conducted experiments to benchmark the overhead of PSec versus a distributed version of P. The first graph shows that creating an SSM in PSec is about 15 times slower than creating a USM in P. And this overhead is mainly because the SSM process creation involves expensive operations, such as provisioning Enclave in the entire attestation procedure. The second graph, showcasing the overhead for trusted sends through SSMs, is a much more smaller approximately 1.2x. Although the creation overhead might seem prohibitively high, we believe that in real-world systems, the usage pattern will tend to revolve more around sends rather than creates. To validate this, we compared overall application level timings of our PSec civitas and OTP examples. The overall application overhead is approximately 3x in just 15 operations and is trending towards a theoretical minimum of 1.2x. We strongly believe that for most real-world applications that perform many operations over their lifetime, this performance overhead is encouraging for the security guarantees provided by using PSec. Before I wrap up, I would just wanted to take a second and say that we dedicate this paper to the memory of our colleague Pramod, who was a brilliant researcher and a wonderful mentor to me personally. He was a prime contributor to this project, and without him, this would not have been possible. That's all for my presentation. I've listed our GitHub repo as well as my email here in case you want to reach out for any questions. Thanks again, and thanks so much for listening.